I'm Olivier. As Antonio mentioned, I work for Disney Streaming, and it's been a while since I wanted to do this talk. I want to talk about a technique that we use at work to, a couple projects to sort of decouple some data types from some serialization formats. The talk is called Revisiting Visitors. I needed a sort of clickbaity title to lure you guys into coming to listen to me. But I hope you have fun. I'm going to start with a story, and it's a story of a hackathon that occurred in March 2019. It was organized by the company. It was involving the London and Manchester office of Disney Streaming. And with a few coworkers, we decided to take on the task of writing a pure Scala AWS SDK. AWS is a cloud provider, and generally, when you want to invoke the services from Scala, you use the AWS SDK written in Java, which is a very good library, but it comes with gotchas that have to do with the Scala language, and you have nullable fields, you have callback-based asynchronous APIs, etc. And we wanted to sort of provide a Scala idiomatic user experience for developers. So we started our hack by looking at the Java SDK, the sources, see how it was sort of built. And turns out AWS supports more than 300 different services. It exposes more than 300 APIs, and each of those APIs have tens, if not hundreds, of methods. There was simply no way that this code was handcrafted. It would just require a very high level of self-discipline to give a consistent user experience to the developers across that many services. So we figured it was code generated, and we dove a little bit further into the Java SDK code base and found those JSON files which appeared to be a specification of the AWS services. Each service had its own JSON file. The JSON file is formed of a top-level metadata field that contains some information that is related to the service. So here we have an example for DynamoDB, which is a NoSQL database provided by AWS. And then you have a list of operations. And each operation has a reference to an input shape and an output shape and a bunch of errors. And all of those are described in the same JSON file. So it's a perfect input for some code generation. We cross-referenced that file with the official AWS documentation that you can find on the website that essentially tells you how operations are serialized as HTTP requests before being sent to AWS. In the case of DynamoDB, the serialization is pretty simple. It's full JSON. The whole entirety of the request that you want to perform to the service is serialized as a JSON payload that is shoved into an HTTP request. The HTTP request is signed using a signature algorithm that I'm not going to describe here, but it's sent to AWS. You get back the response, and the whole data can be deserialized from the body of the response that is abiding by the JSON format. Pretty simple stuff. So what we decided to do was to generate something that would look like this. For each service, you would have a generalized ADT, a GADT, that would correspond to the service, and each of the operations would be represented as case classes extending this GADT. So this is quite a reminiscence of the free monads, which were quite popular 5 or 6 years ago, I think. But the goal is that each operation is going to index or reference its output type without really containing it. It's just reference the data that you're meant to retrieve when you call the operation. And further than those case classes, we would generate the semi-auto-derived encoders, JSON encoders and decoders using Circe as a library for JSON. But each operation would have an associated encoder and decoder, and each of the output of the operations would have an associated encoder and decoder. Because type class derivation and because there's lots of JSON libraries in the Scala ecosystem, doing this was pretty natural. We had 24 hours for the hack, and that was easy enough. Then we sort of came up with this AWS operation abstraction or type class, if you will, that works against our GADT, and that would sort of have a reference to the metadata model that we saw in the JSON that gives you the name of the service and a few other things that are important to formulate the HTTP request. But the more important bit is that the AWS operation would have an encode method and a decoder method that would essentially dispatch to the correct source encoders and decoders based on what operation you were trying to process. So for these tables, when we encode the sort of request, would get the encoder for these tables and essentially pass the instance to that. On the decoding side, we would return the decoder associated to the output of the operation, so that when we get the JSON back from the HTTP request, we could decode to the correct output thing. And using those sort of building blocks, we were able to provide something that looked a little bit like this. So we could sort of define an extension method on our GADT that would take an HTTP client and do everything, serialize the request into JSON, sign it, run it through the client, get the response back, deserialize it, get the result. And that was looking great. We had a demo that printed some sort of or the list of tables that we had in our AWS account, and we were quite happy with it. And we called this project Baguette. The logo is courtesy of Anton Zveridov, by the way. But yeah, my coworkers thought it would be funny to call it Baguette because I'm French, obviously. But it was great, and we actually won the hackathon. And as a sort of prize, we got to go to the Scala Days conference in Lausanne. It was in 2019. Lausanne is amazing. Everything was quite great. But turns out we were extremely lucky when we did that project. And obviously we wanted to take this POC and push it further. But the thing with AWS is that the services that it exposes are or can be categorized in 6 different protocols. And we had selected the simplest one to implement, the JSON in, JSON out. But some of the protocols that AWS supports are much more esoteric or much harder to implement because you don't have as good libraries as you have JSON libraries in the Scala ecosystem. So for instance, the REST-JSON protocol, when you formulate your request, some of the request is going to go to the HTTP headers, some of the request is going to go to the HTTP path, some of the request is going to go to query parameters, and then the rest goes to the HTTP body. Same for XML. There's also this query protocol where essentially the entirety of the AWS request is serialized as a bunch of query parameters before it's passed on to the service, and then you get a blob of XML back that you need to decode into your case class. I sort of lost faith at that point. I really didn't want to have to sort of customize the code generator based on which protocol we were using or going to call in order to support those sort of protocol level aspects. Code generation is a meta-programming exercise. It is not trivial, even though it can probably be considered simpler than macros, but it is definitely not trivial. It is not easy to test. And that was essentially a pet project. So it's not like I had infinite time. So what I figured was that instead of having like 6 different code generators that would customize the code based on the protocol, I would have a single code generator that would output something of an abstraction and then use this abstraction in order to implement the different protocols. So to put it in other words, what I wanted to be able to write was methods like this that would essentially take some instance of something that I would call an operation, that I would have a reference to an input and an output. It would take an HTTP client, and then the implementation of this REST-JSON method would do the protocol, would sort of handle the protocol specific aspects and give me a classly, so a function that returns a monadic, or the result in a monadic context, that would just take the input and give me the output back. And in a separate location, I would be able to do exactly the same thing for the XML version of this. So I wanted to sort of generate protocol-agnostic instances of something that would look like this. The operation references an input and an output. It has a name and a bunch of other metadata. And then you would have an input and an output method returning something related to the type that are indexed. And the question was what is this something? What can I use that is not specific to JSON or specific to XML, but still lets me later on get the information about JSON and XML? So what about visitors? Some of you may have learned the visitor pattern at school or even used it in the industry. But the visitor pattern is a object-oriented design pattern that aims at sort of decoupling data and behavior. And usually how it works is that you have a visitor that is tied to your data model, where each element, each component of your data model is going to have a corresponding visit method, and will also be expected to implement this visitable interface that essentially accept a visitor. A visitor is sort of, well, we're going to see what it looks like, but it's something that aggregates information based on the data type that it traverses or visits. And the data models look like that. Like each instance implements the visitable interface and dispatches itself using the corresponding method. And the thing is, we don't really need it in Scala because we've got such good things for building data models. We've got sealed traits, we've got case classes, and we've got functions to sort of decouple the data from behavior. But visitors respond or work around the lack of sealed traits in languages like Java by essentially offering a constraint to the data model to ensure that whatever modeling you end up doing, you always stay in the guardrails reified by those visitor methods. Essentially, it sort of constrained the data model to this limited set of things that you can visit. And that's interesting. We'll see why. Example of visitor implementation. Blah, blah, blah. We compute the price of a shopping cart, for instance. When we have a cart item, we just return the price of that item. When we have a discount, we reduce the price, or we sort of provide a negative amount. And when we visit the shopping cart, which is just a list of elements being either an item or a discount. Well, what we do is we dispatch we sort of delegate to the accept method from the visitable interface so that the element accepts the visitor and returns the correct implementation there. So we can test it. We sort of build a little instance for a model. We accept the price visitor, and we've got an item that goes for a discount of 1. We get a free. Pretty simple stuff. The problem with the visitor interface is that it reflects a specific model. It reflects a shopping cart, or it reflects a specific bit of data model that can come with some specification. It's not something that you can generalize over. If you want to sort of code against the visitor interface, you're going to code against a specific data model. In our case, it was the shopping cart, for instance. Another problem of visitor is that the data model only appear in contravariant position. They only appear in the parameter of the methods, meaning that you can only consume the data, you can't produce it. You could write a JSON serializer that would take this data and produces a piece of JSON where A becomes JSON, but you can't do the reverse. You can't take a piece of JSON and then rediscover the data from it, recreate the shopping cart. So it's quite limited in that fashion. So the realization at that point was that I couldn't really work at the level of the data. I needed to work at a higher level. I needed to work at the level of data description. Put differently, I couldn't generalize this problem by using an interface that reflects the model. I needed to use an interface that reflects something called the metamodel. And the metamodel is essentially the model for model. It is the set of constructs that lets you create data models, whereas the model is a construct that lets you create instances of data. So for instance, in Scala, you can sort of exemplify the notion of metamodel by saying, well, my metamodel is a set of primitives. It's the notion of case class, which lets me like aggregate data together. It's the notion of seal trait, which lets me express the notion of different things, different alternatives of the same data. You can add the concept of collection in your metamodel. You can sort of list the building blocks that let you create case classes and data models and so on. To further exemplify, well, anytime you have an IDL, an interface definition language, you have a metamodel because the IDL is constrained, sort of limited to a set of constructs that you can use for defining your model. So that's you can say that you have a metamodel for JSON schema, that the proto IDL forms a metamodel, that the avro IDL forms a metamodel, but also looking further than what we are used to in this software development industry, we can think of UML and SysML, which are two metamodels that are actually heavily used in the aerospace industry, in France anyway. So think about that next time you take the plane. Some of the design of the plane probably used UML and SysML tools. It's quite funny. All right, so now the question becomes, okay, how do I work at the level of the metamodel? We know how to work at the level of models. We write functions every day. We need to sort of think at a higher level. Well, we can do it quite mechanically by taking the same concepts we use and getting higher in the kinds. So the kinds, the concept of kind is essentially the shape of a type. We're going to see in an instant, but we're going to start from the shape of our visitor and visitable interface that we saw a minute ago. The visitor has a type parameter. The visitable doesn't have any type parameter, just extends, or we extend it in our data type definitions, where we're going to get rid of those things and recreate them by taking those parameters and lifting them higher in the kinds. So a type parameter that didn't take, that sort of was simple kinded, if you will, that is like integer or string or anything, where we're gonna lift it higher in the kinds, and it's gonna become something that takes a type parameter itself. because it goes from a piece of data to the description of something. As for the visitable, it doesn't have any type parameter, so we're giving it one essentially. So to sort of explain it a little bit differently, this syntax here means that this visitor is going to accept as a type argument anything that itself takes a type parameter, in the same way that some functions accept functions as arguments. All right, so because we don't want to sort of overload the terms, we're ditching the names visitor and visitable. And the names that I came up with was schematic and schema. They are absolutely terrible names, or schema isn't, but schematic is probably a terrible name. Naming things is hard, so yeah, definitely please find another name for this. But essentially, that's what we call it at work, and it's basically just a higher candidate visitor. All right, so back to our concept of operation, which works against an input and output. Well, now we know that we have something that's going to have the correct shape to be referenced in the operation, and that's going to be the schema, the thing that is equivalent to the visitable, except that it works at the level of description instead of data. So what is the schema? Well, in a similar fashion, we're going to go through the same exercise of taking this visitable thing and changing it so that it works against descriptions of things. So we saw that visitable gained a type parameter and we renamed it to schema. We're renaming the accept method to derive. You'll see why in an instant. There's a that represented some data that we want to output. Well, in our case, we're not going to want to output data anymore. We're going to want to output a description of data or a codec of data, which is why it's turning into this codec type parameter that takes a type parameter itself. And then the visitor became this higher candidate visitor thing that I call schematic, but it's exactly the same argument translated or going through this translation of going higher in the kinds. And instead of the data here, well, we sort of combine the things together. We've got a codec that takes a type parameter. We've got this data. Well, it's going to output a codec of the data. All right. So trying to formulate it differently, given a schematic of codec and a schema of data, we gain a codec of data. And the codec is essentially the protocol-specific concept that we're going to implement against, whether it's JSON or XML or some sort of query parameter encoding. The data is your case class as usual. It's your list table output, your list table requests, etc. So the concept, in a similar fashion that visitor aimed at decoupling the data from behavior, well, the schema and schematic couple, or the schema and schematic sort of combination decouples data from codecs. I'm going to repeat or try another explanation as well. Usually when you sort of deal with any sort of serialization in Scala, you're going to do something where you're going to define your data model, and in the companion object of the data model, or using this derives keyword from Scala 3, you're going to implement some instances of encoders and decoders for this data type. But that sort of, because you're using the companion object or because you're using this derives keyword, you're essentially creating this coupling of data with whatever format you want for it to work against. In our case, we don't know what format we're going to be working against, because the code generation is responsible for creating the data, but it's not aware of whether it's going to be working in JSON or XML. So we're removing this coupling, and conceptually speaking, it's not really working this way because we're using code generation instead of macro-based type class derivation or the derives mechanism from Scala 3. We are deriving a schema from our data model, and we can regain the codec by combining the schema with a specific schematic implementation, which this decoupling enables protocol agnosticness, because if we go back to this operation interface there is absolutely no reference to a particular XML or JSON type or concept. It also takes things further, and it allows you to decouple your data models from third-party libraries, so that this pattern, even if you work in the context of JSON, for instance, you have the freedom of selecting the JSON library that you want, and the generated code isn't heavily married to a specific ecosystem or JSON library, which is something desirable, in my opinion, when you sort of try to offer code generation. So this sort of operation abstraction, that is something that we want to, or instances of this operation, that is what we want to code generate, because that is what the IDL, the piece of JSON that we saw at the beginning, has knowledge of. We had a list of operations, and each operation had an input and an output, and we knew what shape it was using. So when you do your code generation, you need to sort of generate those instances of operations. And you need to generate the visitable, essentially. You need to generate the data type, and you need to sort of generate this derived method, which came from our schema abstraction. So the schema takes or references a piece of data, and as a refresher, it has this derived method that takes an abstract codec or as a type, and a schematic. Oops, I should have named this differently here, but a schematic implementation that is specific to that codec and gives us a codec of person. We don't know what the codec is going to be here. So we're going to see, like, obviously this, because everything is abstract, the only way that we can formalize this codec of a person is going to be by using whatever this schematic gives us. We're going to see about that in a bit. But that is what is code generated. The data specific aspect of what you're trying to achieve is what needs to be code generated. Then elsewhere in some opt-in SBT module or whatever, opt-in library, you're going to take care of the codec specific logic. You're going to implement those schematic encoders, schematic decoders. Those things do not have any knowledge of the models we're going to be working against. They're going to be working against a number of methods. Well, we're going to see about it. I'm sort of teasing a little, but I really want to try and take you through the sort of process of thoughts that led to this pattern, recreating the pattern as we go. So once you have the schematic, and you can write a generic instance of methods like this, where you're going to use the schemas that are part of the operation, and for each of them derive the codec that is relevant for the input or the output. So in the case of DynamoDB, for instance, we were encoding the output, encoding the input in JSON, decoding the output from JSON. So what we're doing here is taking the schematic encoder, which works against a JSON encoder, and running it through our schema, which gives us an encoder for the input. Same for the output, we derive a decoder for the output. And then with a little bit of wiring, we manage to create a sort of high-level classly-like function that will take my list tables code-generated thing and output the list table output case class that was also code-generated. It's like the high-level domain-specific modeling of those operations. All right, let's talk about what schematic look like. So metamodel. So the schematic depends on your metamodel essentially, in the same way that visitors were coupled to models. Schematic, or the higher kind visitor, is coupled to the metamodel, and you can think of them as algebraic constructs. So you have a bunch of primitives, you have a bunch of operations that take smaller elements and combine them together. Additionally, in your metamodel, as I hinted before, you can add any number of concepts that let users define data models. It can be collections, the concept of enumeration. You can allow for recursion or disallow for recursion. You can add arbitrary annotations to your data models. So we're going to use a toy metamodel as an example where we'll just have integers and strings as our primitives. Sorry, the sun is coming directly to my face. We'll allow for our models to have lists, and we'll allow for product of arbitrary 2, so case class of size 2. We start our definition of our schematic algebra by listing each primitive, and for each of them, we have a method that doesn't take any type parameter because it can't be divided in smaller building blocks, and it outputs a codec of whatever it works against. For the list, well, it works very similar to what you get in usual type class derivation, namely this schematic interface provides you with a method that says, if I'm able to, or if I have a codec for my type A, then I can have a codec for a list of A. That is sort of typical derivation induction. Then for product, it becomes a little bit more like it becomes a little bit hairier. So we're going to have a look at the specific example of JSON to get a sense of what we need. So this person case class here translates naturally to this bit of JSON. Pretty simple stuff. So what if we try to implement this using Cersei, for instance? Let's try and find out exactly the sort of important bits that let us do this. So for this case class person, we create a JSON object, and for each of the fields, we create an entry in that object that has label and dispatches to the correct encoder by retrieving the value. So the important bits for the name of a person, for instance, in order for this data to be encoded, is the presence of the name label, the presence of the encoder that works against the type of this field, and an accessor that goes from the case class and let us get the specific value of that field. It's exactly the same thing for the age field. If we try to create a sort of construct that is going to let us hold all of those three things together, we are going to call it field. We'll need the label, the encoder, and the accessor. If we try to generalize this, it would look like this, where you have the label, you have a reference to the int method that we defined earlier in our schematic interface, and you'd have the accessor that lets you go from a person to the value. So that's what the field construct looks like, where you have like this abstract codec that works against the type of the field. You have something that lets you get the value of the field from the product type, and you've got the label, which gives us this abstract method in our schematic interface. That's our schematic interface that reflects our little toy metamodel. which means that now we can express the derive method for our person case class, person as a name, and an age, and it's a product type, it's a case class. So we call the product method from our schematic here, and we pass a field instance for each field of the person. And the types are just going to align magically because we're outputting codec of int in the schematic int method, codec of string in the schematic string method, and provided we have fields that index two different types, we get we get sort of the codec of this here, this type here, the product type essentially. We are missing something in this product abstraction, because our schematic interface acts as an abstraction that lets us recover the implementation of specific codecs, meaning that it should be able to handle both the encoding side and the decoding side, and we've just cared about the encoding side of things until now. So we are going to do the same exercise for decoding, and essentially you write a decoder for person by sort of getting the, so in Circe it's like you have this cursor which tells you where you are in the JSON, and what you do is like, well, do I have a field name? If so, I'm going to dispatch it to a string encoder. Do I have a field age? If so, I'm going to dispatch it to an int encoder. And if I manage to sort of retrieve values for both those things, I'm calling the constructor of my case class. And we haven't captured the notion of the constructor in our abstraction. If we do, all we need to do in order to complete our product method is basically take this additional type parameter that, this additional function parameter that expresses the construction of the product type from its individual component. Namely, you've got a field of type A1, a field of type A2. You're able to recreate the type P. So the full schematic abstraction for our sort of metamodel, our constraint metamodel, looks like this. It has methods for all of the primitives that we care about. It has a method for the list type, and it has a way to sort of take separate fields and combine them together. And so we can sort of complete the implementation of our person schema by adding the person constructor as such. Then we can sort of use that person schema and create some more data models. Like here we have a team. A team is a name and a list of members. So we do exactly the same thing that we did, namely the field name is going to be roughly the same, but the members, well, we've got a list now, so we call the list method from our schematic abstraction here, and we pass it the result of deriving the codec for the person. And we pass it the accessor that lets us retrieve the list of persons from the team case class, as well as the constructor of the case class. Right, so here I'm going to switch real quick because I don't have much time left to this VS Code session. Just checking that it compiles. It doesn't. There you go. So there we have the code that I just showed you. We have the field, we have the schematic modeling of our metamodel. We've got the concept of schema. We have modeled the person and created the schema for that person. We have done the same thing for teams. And then we have some schematic implementations that are specific to JSON. We've got an encoder here, and we've got a decoder here. And for each of those methods, essentially, we recreate what it means to encode an int and encode a string and encode a list of something, etc. So if here I've got a little demo. Okay, so what I did here was using this person schema to derive an encoder for person and a decoder for person here. And I'm just running it through this little program to check that it behaves correctly. You can see that this person here gets encoded as such in JSON and decoded into the same piece of data. And we also implemented a schematic instance that essentially gives us a string representation of our data models. And it doesn't know what data models, it just knows that the data models that it's going to work against are expressed in our metamodel. They are expressed only with the building blocks that we are allowing for, because we're able to provide an instance of this abstraction here. So if we write the representation of the team data type, that's what we get. Right, I've got 4 minutes left. This is a very tight squeeze. Okay, right. So we've sort of managed to find a pattern that lets us decouple data and use cases and sort of codecs, serialization codecs, which means that we can implement the various AWS use cases in isolation without touching the code generation. We can also go further than that and have an explosion of different use cases for the data models that abide by this pattern. We can provide Scala check random generators for this data, pretty printers. We can provide CLI options, like something that would sort of provide you with a CLI user experience for this data. We can provide GraphQL schemas or protobuf codecs, etc. It sort of gives you an explosion of use cases. So now it's the last phase of pros and cons of this pattern. The cons is obviously that it sort of acts as a constraint over your data model. You need to think ahead in terms of the building blocks that you're going to allow for when you define data models, which works extremely well when you have an IDL, because the IDL is already constraining the data models that you are able to express. But when you start using this pattern, evidently, if you sell it to other teams or other people are going to be like, oh, why can't I do this or why can't I do that? Because we're sort of locking in, we're sort of constraining the data models in order to gain an explosion of use cases. Whereas usually people are used to have one use case provided by a library and some type class that lets them come with any type they want, so they can sort of have the freedom in using an HTTP client with some sort of weird data model, as long as they can provide a JSON encoder for it. The pros are that adding new use cases is essentially always the same kind of effort. The bounded effort, it's really easy just implementing an interface. It respects the tech choices of your users. It doesn't really force your user to use a specific library if they want to use another one. I think that's a good thing. It is applicable to Java. Even though Java doesn't have hierarchy types, you can take the same pattern and modulo some unsafe casts, gain exactly the same thing. And we actually do it at Disney Streaming. And yeah, it works great with IDLs. I've got 1 minute left. So this talk was essentially just to describe a pattern that we use. Essentially, AWS has released an IDL that's much better than the piece of JSON that we saw early in the talk. It's called the Smithy IDL. It's really, really well designed. I encourage you to have a look at it. It's really interesting. And now, these days, they are modeling all of their services in this IDL. so we decided to sort of get rid of Baguette. Unfortunately, it's such a cool name, but we're sort of put it in the bin, and we recreated a similar thing that works against Smithy. It's called Smithy for us. It's available at this address or on GitHub. It provides you with like automatic HTTP clients and servers for your services that are defined in Smithy. Yeah, please go have a look.